This video is made possible by Google. The Maths Inside Your Fonts by Laurence Penny.
Okay, hello everybody. I'm Laurence Penny, and today I'll be talking to you about the maths inside your fonts. And by your fonts, I mean fonts that you use every day, as well as fonts that you might make as type designers and font engineers. So it's going to be a little bit personal, this talk. There's me, around age 11. I'm going to start with myself as a kid. What I loved back then, more than anything, well, apart from racing cars, was these three things. I loved maths, I loved letters, and I loved maps. I was lucky to have great maths teachers. But as for the lettering, my art teacher wasn't that into lettering or typography. The maps, my geography teacher, he had no passion for maps, unfortunately. So for the maps, I had to keep myself busy. So I bought these, one of the things I did was buy these adventure game books where you could choose your own route through the book. And embedded in these books was a kind of map that I would draw based on reading this plain text book. I'd draw a nice lettering on the top, on the book as well, on the map as well, and sell these to my friends at school. So that was fun, and I still love maps. But how about maps and letters? Well, a little bit later, I kept myself busy with, I started to wonder about the mathematical aspects of letters. So as I looked through specimen books, I thought about the underlying rules that lettering artists used and type designers used, and how they could be captured as maths, as digital objects. And could I capture these rules and save myself some time creating the fonts? And I thought about elliptical arcs. To get the varying curvature of, obviously circles wasn't going to be enough. Then I did more reading. The web didn't exist yet. And I found out about Bezier curves and all their amazing properties. So what kind of maths is in fonts? Well, the fundamental thing is obviously geometry. One of the foundations of mathematics is geometry, but you've got all these other aspects as well. So I'm going to talk about some of these today in my talk. So I want to talk about a variety of mathematical ideas and formulae are embedded in modern fonts with implications for performance, saving data, and powerful creativity. And I'll try to stay focused on the maths, for the most part, skipping over the engineering and the computer science. So it starts quite a while ago with these constructed letters. And applying mathematics to letter design goes back to at least the Renaissance, to these writing masters. Feliciano, Pacioli, Dürer, Torri, and others, they came up with mathematical schemes to draw what they regarded as perfect Roman capitals. In style, they resemble the ancient Roman architectural theories of Vitruvius, which would have recently been printed for the first time. Vitruvius likes to declare correct ratios between the width and height of a column. The writing masters did the same for letter stems. Thickness to height should be 9:1. Or 10:1, depending who you listen to. I think it's quite possible that the Romans themselves had such diagrams and formulae. What all these show is a reverence for the circle as the only curve. It makes sense, as it is trivial to construct with a compass, and there was something sacred about the circle from its use in astronomy. Torri warned that the geometry should be spelled out. Diagrams alone were not enough. And I'll just read this out. I've come to the conclusion that if Euclid, the prince of geometry, returned to this world of ours, he would never find that the curves of the letters could be so constructed by means of circles made with compasses. That's Cresci, 1570, who was a great Italic writing master. A couple more that are worth checking out. Here's a constructed Roman alphabet by David Goines, dating from 1979, first as a poster, and that became a book, and the book is now a very nice website that you should check out. The text exemplifies the kind of mathematical expression that was often used in the Renaissance and classical times. It's rhetorical mathematics, using plain text to represent a kind of program for drawing. And finally, a last example is Rosberg's system of creating a fraktur alphabet, amazingly from 1793. It uses a modular system of parameterized rhombuses and spirals, which are drawn with a pen of variable angle. Peter Knuth has explored the work and calls it the very first variable font. She has made a variable font based purely on Rosberg's work, and do watch her talk on YouTube. In 1977, the eminent computer scientist Donald Knuth set out on an incredible burst of activity in type design and typesetting, presenting it in a 1978 lecture. He had become frustrated by the declining quality of mathematics publishing and decided something must be done. He soon decided on how he would approach computerizing typesetting, and that became TeX and LaTeX. But type design was less obvious. And here he looked at early digitization systems, such as Icarus, and decided he would take a different path. Making a copy was not penetrating to the heart of the problem, he said. He came up with the Metafont glyph programming language. And it has the usual things you expect in a language: branching, looping, functions, math operators. The cool thing is it can define a pen shape and then sweep that shape around a curved path defined as a cubic Bezier curve. This slide shows the Metafont program for ampersand in the computer modern family. It generates numerous different styles of the glyph, depending on input parameters. This typeface superfamily, indeed Knuth's whole system, remains widely used in scientific publishing today, and I'm about to use it in this talk. The alarm bell is that only a tiny handful of type designers ever mastered Metafont. They couldn't be persuaded to write these programs. Yet thinking of fonts as parametric would make a comeback. So we just mentioned Bezier curves. What are they? They were invented independently by two French engineers around 1960. They're pretty intuitive to manipulate. They can be joined together very smoothly. They approximate circles well, and they're efficient on slow computers. And if you define a glyph outline with straight lines and Bezier curves, there's nothing hidden in code. Glyphs are essentially CAD drawings. There's no model for curves of varying curvature that's been more enthusiastically taken up by designers, by non-mathematicians. And these are the formulae for the cubic and quadratic Bezier curves. Adobe chose cubic for PostScript Type 1. Apple chose quadratic for TrueType. And this video shows the same set of control points rendered as a cubic on the left that you're familiar with, a quadratic curve, dropping the second off-curve point. When you export a font, by the way, your font editor approximates these from your cubic curves. And finally, on the right, the double quadratic curve that TrueType handles. We're back to 4 control points now, and you can use these directly in some font editing apps, including RoboFont. I want to talk about vectors a bit now. Vector, what I mean by a vector is a relative point movement. So it's two numbers that declare how far you move to the right and how far you move upwards. So what's your x difference and what's your y difference, your dx and your dy. And both of the major font formats use vectors. They're relative, not absolute, to store the points of a glyph. To find the location of point 3, you take the sum of vectors 0 to 3. And vectors tend to be smaller numbers, so take up less data when stored. They're also nice if you need to reuse a section of a glyph as a component. You simply move the start point. Quantization. So we have our scalable CAD drawings. How do we get them to computer screens? Well, we need to scale them, then rasterize them to the pixel grid. The coarser the grid, the larger the pixels, the lower the quality, eventually to the point of illegibility. And to give an idea of how things have improved, the best modern phone has 640 dots per inch. So you could get 80 of those phone pixels inside one Mac pixel. Document I reference at the bottom, The Raster Tragedy, is the classic review of the issues. It's really worth reading. And quantization is a tricky problem to solve, since a dumb rasterizer just fills in shapes. Mathematically, these are fine, those pixel patterns. To humans, they're not. Those two outline circles are identical, yet produce different pixel patterns. Same for those two identical stems on the H. We tackle the problem with methods known as hinting. Essentially, they check the grid coarseness, then move glyph points around in a clever way so that a new distorted outline gets filled with a nicer pattern. For example, if we align the leftmost and topmost outline points of those circles to the grid, we would get identical patterns. Then we might control each circle's width and height, ensuring the patterns are symmetrical. Same for the two stems of the H. We choose certain distances to keep under control and abandon other distances. Several different hinting technologies emerged in the late 1980s. Apple was a few years late when it presented its approach to hinting. Adobe and other font companies were already hinting fonts with their own techniques, and it was therefore important for Apple that fonts already hinted could be translated into its new concept, TrueType. Their solution was to design a programming language so that font engineers could still tackle the raster tragedy using arbitrary methods. And it is a real language, having variables, branching on conditions, looping, and functions. It has arithmetic operators, add, sub, multiply, and divide. It also has special operators to align points, measure distances, make distances match a lookup value, and other things, interpolate points as well. It also has a brilliant way to handle diagonal strokes using vector projection. Points move along the freedom vector, but are measured against the projection vector, which is great for diagonals, as I say. It's remarkable to realize that this all worked great back in 1991 on a Mac Classic with an 8 megahertz processor and 1 megabyte memory. Here's an A glyph shown before and after the hinting program has executed. Now, all of this is pretty well known, but the raw mathematical abilities of TrueType are occasionally put on show. Here's a very special font that displays the internal values of a variation axis as the user adjusts a slider. That number you see changing there is a single glyph. Doesn't seem possible. But how it's constructed is from this bizarre glyph on the right, which contains all of the digits 0 to 9, the plus and minus symbols, plus a period. The TrueType program in this glyph checks the current axis value, converts it into a decimal using TrueType's math operators. Then to display the number, the program collapses to the origin all the parts of the glyph that it doesn't need. So we come to variable fonts. They were invented by Mike Reed at Apple around 1992 and incorporated into TrueType. It took the 2016 reboot, though, for them to take off. You've seen talks about them before, so I won't do another one now, but I will point you to this excellent article by Tom Rickner, who was at Apple at the birth. And I will talk a bit about vectors in variable fonts. Designers think in terms of masters or sources when they create a font family, but we can also think of the difference or delta in location of each point in a bold font as related to its location in the regular as a vector. This turns out to be a great way of storing the relationship of one glyph to another. Now, if we take the deltas and multiply all of them by a value between 0 and 1, we call that the axis scalar, then add them as vectors to each original point, we interpolate from one glyph to another. We interpolate from regular to bold, for example. So what happens when we get multiple axes? Let's visualize it. This is Samsa, an app I wrote to expose the maths inside variable fonts. Here I've loaded a font with weight and width axes, and as I use the sliders, watch the arrows. The weight vectors are brown, width vectors are pink. Each arrow's length is based on the position of the associated axis slider, treated as value between 0 and 1, multiplied by those deltas that we stored in the font. Note how each arrow never changes its direction. It's only its length that changes. But there's also a green arrow. This is the combined weight-width vector that acts as a kind of correction for the extreme black-wide instance in this case. See how it responds in a slightly different way to the other arrows? Its magnitude is proportional to the product of the axis scalars. So if you look at those values highlighted in green at the bottom left, when the axis scalars are at 0.5, the green scalar for that combined green arrow is at 0.25, which is 0.5 times 0.5. And this is the maths that lets multi-axis variations work so beautifully and efficiently. This talk, in the slide up there, given at Typo Labs 2018 by the Underwear Group, was truly groundbreaking, one of the most impressive talks about fonts we'd ever seen, and everyone should watch it. So HOI stands for Higher Order Interpolation. The fundamental and unexpected discovery was that if you adjust multiple axes in a variable font, keeping them in sync, then the control points of a glyph move along curved lines. When set up correctly, the curves can be specified precisely by the type designer. It really blew minds, and Underwear continues to push it to new things. Do check out their video of the Chinese character Biang, beautifully animated by HOI to show its 58 strokes being drawn. Here's an example. And this is a single glyph from a totally valid OpenType font whose axes are simply being moved in sync, causing movement along curves. But as well as producing these amazing animations, HOI also solves various genuine design problems very efficiently. And here's the maths. The key thing to look for there is that third line, where it says equals t and then some brackets. There we're factorizing out that t value from the parametric equation. That's the key step. And then you can use that to work out what delta values you put into your font. I recently asked Mike Reed, who invented variations, what he thought when he first saw Hoi. And his answer was just, wow, why didn't I think of that? It was hiding in there all the time, a real mathematical discovery. So we know what a design space is. We can visualize 3D design spaces quite easily. And here's the Knuth's I-cube, a highly influential visualization. But 4 dimensions are already hard on the brain. Here's an attempt at projecting a 6D space into our world, made by a carpenter I know. Some modern fonts have 20 or more axes. We can think about them as 20 independent variables, perhaps, and that makes it a bit easier. But still, variation maths still truly handles it as a 20-dimensional space, and that takes some discipline to work with. And it gets more complicated. People realized already in 2016, when axes combine, even in the simple case of a weight and width font, the bold condensed might not be at the same weight value as the bold, and neither of them at the proper value for bold, which is 700. The 2 axes need somehow to affect each other. Another idea brewing in 2016 was David Berlow's concept for parametric fonts. And here is Amstelvar, a font, its current version, in 27 axes. These are OpenType fonts that use variations to control specific aspects of the design in a highly calibrated way. Choose a precise vertical stem thickness, or X height, or serif length, for example, all measured in font units. Although hugely versatile, these fonts are difficult to control. Offering 27 axes to end users is never going to work. But what if the weight and width axes could control the parametric axes? The solution to both these problems is to enable design space distortion. And a super compact method of adding distortion was added to OpenType by Bedad Esvabod a couple of years ago. It uses variation maths itself to do these distortions, and we call it AVAR2. It's publicly documented on GitHub. So design space distortion, especially of large numbers of axes, calls for a new kind of visualization. And this is my own Fencer app, which is public, like the Samsa app I showed earlier. And it uses mappings to create these distortions. A mapping, let me just start that going. A mapping pulls the space from one position in multi-dimensional space to another. And the app shows 2 axes at a time in a window, but you can have multiple windows open at the same time, each window looking at a different slice through that multi-dimensional design space. The same space, the same mappings, but from different viewpoints. It shows mappings in green, named instances in red, and the blue icon shows how a certain point in the design space is displaced as we move around the distorted space. In fact, playing with axis distortion made me wonder about how AVAR2 technology might be useful in other dynamic systems of many inputs outside our little domain, such as engine control units, flight control systems. I actually have a call coming up with a quantum cryptography friend to discuss how AVAR2 mappings might have a place in quantum maths, where higher dimensional math is everywhere. Last one, another video from Underwear. This is, again, a real font, this time using Color V1 for its marvelous colors, and AVAR2 to handle that single dial at the top. So that's the only input axis, is that dial at the top. And that dial adjusts several, so that direction axis. So that direction axis is changing the locations of the gradient locations in this case, which is having a wonderful effect of making it look like the sun is moving around the lettering. Turing completeness. I won't spend much time on this, but it feels important to mention since Alan Turing is such a hero to mathematicians as well as to computer scientists. A Turing machine is a theoretical computer imagined by Turing in 1936 that in principle can implement any computer algorithm. And we say a system is Turing complete if it can simulate a Turing machine. It turns out that all of these font technologies are in themselves Turing complete. I'll just go through them. Metafont, well, that's not surprising since it's a programming language. Type 3 fonts, I won't get into them, but that's another programming language. TrueType, again, the hinting language is a programming language, so that's not too much of a surprise. But it did come as a big surprise about GSub when people realized it is also Turing complete. And what GSub does is take an input sequence of glyph IDs and transforms it to an output sequence of glyph IDs. That's what it does, depending on your current script and some feature settings. That came to it as a big surprise, even to seasoned font software engineers. AAT is Apple's kind of loose equivalent of GSub, and that turns out that's also Turing complete. And these last three, they exist in many current fonts, and that means a modern font system emulates 3 separate Turing machines, which is quite something to think about. It's nice to know if you fully implement OpenType, then you necessarily create 3 little computers for fonts to run their programs on. And maybe soon there'll be a 4th. This is an extra little component that I know Simon over there is keen on. So another place where we might get a little computer running inside the font. So I did think I'd be a type designer once, and I think I don't really have enough patience for that. That's why I like to make tools where explore typeface automation and visualization instead. And I probably don't have enough talent either. But that perhaps leads to an overall lesson that there are plenty of roles for many different types of people in our craft, in our business. I see people who don't get the maths inside fonts, and I like to help them understand what's happening so they can get their jobs done, for one thing, but also so they can exploit the technology more creatively. I'm going to leave you with some homework, which is read Knuth's 1978 paper, dive into the beautiful properties of the Bezier curve, read The Raster Tragedy, watch Petra's talk about Rosberg, do read Tom Rickner's article, watch Underwear's Hoy talk, get to grips with Berlow's parametric system, and distort some design spaces. And most important, embrace joyfully those obsessions of your inner child, especially those your teacher didn't get. Thank you very much.